Hello, welcome back to Learning with Ms. H. Today we are in Earth Science and we're going to be talking about plate tectonics. So you're going to learn about how tectonic plates work, what they are, how they move, how they fit together, all of that, and be able to explain that. So for your bell work in your notebooks, give me a short paragraph explaining what a supercontinent is and what some of the past supercontinents were called, as well as when they existed. You should remember this from our History of the Earth unit. If you don't, feel free to go back and look that information up to be able to do this spellwork assignment. We want to make sure that you can make the connections between what we're learning now and what we learned before. You'll have a homework assignment, which is linked here. It's also linked at the bottom. We're going to talk about this homework assignment first, so that those of you that want to do the notes on your own can go ahead and jump off, get that taken care of, and then get started on the homework assignment. So this is a PDF. So there's a link here. If you click this, it's going to have you make your own copy of a Google Doc. And when you do that, it's going to look like this. So this is your plate tectonics answer sheet. It has questions and then the answers you're going to write down in these areas. It's numbered for you already, and all of these match up with what is on this PDF form. So you've got a question box here that you can fill in for questions about plate tectonics, and then you have your questions that you're going to answer down here. 23 points. Make sure that you are uploading the file. You'll upload this Google Doc when you finish it. So just type your answers in on the correct number. And then if you have any other questions that you think might be asked about this, you can type those in up here. This is your question box there. So that is the homework assignment for today. Go ahead and take a look at that when you are ready. If you're going to take notes with me, we're going to go ahead and start on our plate tectonics notes here. Excuse me. So go ahead and pause the video, get out something to write with, write on, do your bell work, and then rejoin us to go through the plate tectonics notes. All right, welcome back. Hopefully you got your bell work done and you were able to make those connections between tectonic plates and the supercontinents that we learned about in the previous unit. We're going to go through these notes together, and remember that you can pause this video at any point in time to finish up a slide that you're on and play catch up a little bit, and then restart the video when you're ready to move on to the next slide. So what we're starting off here, this very first slide is a map of the tectonic plates. You're not going to do anything with this right now, but one of the upcoming lessons, you're actually going to recreate this map on your own paper. And then we'll place the continents on top of it, and eventually we're going to place in fault lines for earthquakes, where the earthquakes happen, and we'll place volcanoes on here as well. So you can see how all of this relates, the boundaries of the plates, how those relate to volcanic activity and earthquake activity. So you will get very familiar with this image. So here's a list of all the tectonic plates. These are the major ones. There are some minor plates that we're not going to worry about. These are the majors. Some of them you can see are still pretty small, even though they're considered major plates. We're not going to necessarily worry about every single one of the teeny tiny ones, but the ones that are in this image we'll probably put on your map. So Antarctic plate is one of the largest. It's down here at the bottom. Then you have the Pacific plate, is this light blue, and it actually, if you take this map and you connect the two sides of it together, so you fold it into like a cylinder almost, you'll actually be able to have the top meet together and the bottom meet together, and it will make like a ball if you were to cut this out and put it together that way. So you can see that anything on the left and the right are actually going to connect up and be the same. So you have this North American plate right here in the kind of light yellowish beige color that is also over here, and the same thing with the Pacific plate. The Australian plate, you have a little piece of it over here on the side. So Make sure that you are kind of paying attention to how they connect up on either side of the map. Again, you're not going to have to draw anything right now. You're going to have a larger picture to work off of and some instructions, and that's going to be in a future lesson when we make the map for you. So when we talk about plate tectonics, what do we mean? Well, a tectonic plate is a piece of the crust. It's like a puzzle piece. So the entire crust of the earth is broken up into these little plates, and they float around on top of the mantle and move around. Remember we talked about the lithosphere in our last presentation, our last lesson. So that lithosphere is what we're talking about. Those are the tectonic plates. The very, very top part of the mantle hooked onto the crust of the earth, broken apart into pieces. It moves around and floats and connects together like a jigsaw puzzle. How does that work then? So it works by what's called mantle convection. Remember that middle layer of the mantle is kind of that Laffy Taffy layer where it's pliable and moldable, so you can pull it and stretch it and push it back together and squeeze it together and make it into something that's not really a solid but not really a liquid. It's kind of that weird in-between silly putty kind of state. It's moving at all times. Remember that it moves as fast as your fingernail grows, so very, very slowly. But we have what is called convection going on in there. So if you think of a conveyor belt at the checkout line of the grocery store, it comes up, it moves down the line, and then it goes back down, and it swings back around. And it just keeps moving like that in a circular motion. That's called convection. That's also how convection ovens or traditional ovens work as well. And the heat comes in and it circulates around. So when you have convection going on, you have that mantle moving in that circular motion, and anything that's on the mantle is going to move with it. So where it comes up and then pushes out, it's going to push out whatever is actually on top of it. So if this is floating here, this comes up, grabs on here, pushes out this way, and then back down. Comes up, pushes out this way, and then back down. So it's going to move things around. Hot rock is going to rise, so the hotter it is, the more it's going to rise. Cooler rock is going to sink to the bottom. And we know that the mantle gets hotter as you go further down, so you have that hot rock on the bottom that's always going to rise up and move along the top, losing its heat as it goes. Once it gets cool, it sinks back down, picks the heat back up as it moves across, and then comes back up as it gets hot again. So it's just going to keep doing that repeatedly forever, and that motion of convection is what causes those plates to move. The convection is going to happen in opposite directions. When you have two cells next to each other, they're going to kind of move towards each other. So they come from out here moving towards each other, so you're going to have things moving out away. You're also going to have a spot on the other side then where things are moving down instead of up. So in this image, you have upwelling where they're going towards each other and moving up. If you go to the opposite sides of those images, things are going to be moving down as they get closer together. Plate boundaries. This is exactly what it sounds like. It's the boundary of a tectonic plate. It's where the edge of that plate is at. We've got a couple different types we're going to talk about, and it's based on how they fit together and how they move next to each other. So a plate itself is fine. It's not going to cause an earthquake if it's by itself. When it gets next to another plate, it can cause problems like earthquakes, volcanoes, depending on how those two plates interact with each other and move around each other. So that's where we're going next. We're going to talk about the three different types of boundaries. Divergent is first. Divergent, if you're not sure what that means, it means moving away. So two plates are going to be moving away from each other. So it's the middle of this picture here where those two plates are, the convection is coming up and then moving out away from each other. So you have this spot right here where it gets pushed up from the convection going up, but then it moves out away in each direction. So this is going to be your divergent boundary. The other end, it's going to move towards each other, and that's going to be convergent. And then when they move side to side and kind of rub against each other, like you were rubbing your hands to get warm, that would be a transform. So let's take a look at divergent first. So you have two plates moving away from each other, so that you're moving up and out. This causes what we know as seafloor spreading. A lot of these divergent boundaries are going to happen underneath the ocean. So if they do happen under the ocean, it causes the seafloor to spread and move out. So it comes up and pushes away. If it happens under the land of the continental crust, it's going to cause what is called a rift valley. So it's going to cause basically a crack in the crust. So it's going to look like a hole in the crust. Because you have this uplifting spot, this hot spot where it's coming up and pushing the crust out away from itself and separating it. You can have ocean ridges, you can have volcanoes, you can have rift valleys, all kinds of different features at these locations. And you've got some images here that are a little bit more clear on your own Chromebooks than they will be on this video of divergent boundaries happening and these pieces of crust moving away from each other. So the next one then is the convergent, where they're moving towards each other, and you've got a couple of different ways this can happen, and there's some different things that will happen depending on what types of crust are coming together. So it is always two pieces coming together and bumping into each other. Instead of moving away, they're coming towards each other and crashing. When they crash together, what happens to them depends on the density of the crust. The more dense crust is going to go towards the bottom, and the less dense crust is going to kind of skim along the top. So we can have ocean crust or continental crust. When we have a piece of oceanic and a piece of continental that crash into each other, the oceanic is more dense, so it's going to subduct or go underneath that continental crust. That is called a subduction zone because you have one piece going underneath the other one. This type of thing is going to cause things like volcanoes, trenches, earthquakes, when you have subduction zones where one piece is going underneath the other one. Second type of interaction, you can have two pieces of oceanic crust. So if you have ocean and ocean meeting, you're going to have volcanoes, you're going to have island arcs, and oceanic trenches. And you'll still have one going underneath the other with a subduction zone there, but you're going to have a different, the densities are going to be a lot closer together, so you're going to have those different outcomes here. So the top one, you have continental crust and oceanic crust meeting. Oceanic goes underneath. Continental skims along the top. We get our subduction zone with volcanoes and trenches and earthquakes and all of that. You also get these mountains here because it kind of folds up a little bit as it crashes. Ocean to ocean, so you'll see that instead of meeting right here along the edge of the land, it's meeting up way out here in the ocean. So we don't really get the mountains here, but we do get these island arcs happening near where it's meeting up. And that's because you get volcanoes, and the volcanoes are hot spots, and they will erupt, and as they reach the surface, they'll cool, and that will create these islands. We'll learn more about those specifically when we talk about volcanoes. The last one is if you have two pieces of continental crust, and that's this bottom image. So you have two pieces of land crashing into each other. This one, you get the really high, wide, thick mountain ranges, way more mountains in this one than you do in the ocean continental. Anytime you have continental crust involved in the meeting, you're going to get a little bit of hills and mountains. But this one is massive amounts. So when this happens, you're going to have mountains like the Himalayas that are these big, long mountain ranges. You still have subduction here. One is going underneath eventually, but they get pushed up more so than they get pushed down. Our last boundary is the transform boundary, and this one is the one where it's like warming your hands. The two tectonic plates rub against each other, side to side. So this one, the San Andreas Fault out in California, is an example of this one. You get lots and lots of earthquakes when you have this type of boundary because they rub, and as they rub, those rock edges get caught When they get caught, you get tension, and eventually they're going to slip, and that's what causes those earthquakes to happen, is when the rocks slip off of each other, or they'll bend and then bounce back. So they're kind of grinding their way past each other, like if you're rubbing your hands to get warm. You'll have separation and division, so you'll have features that may be offset from each other. If this was one connected mountain range here, and then you had this earthquake happen here, it would offset the mountain range. So it would start down here and end way up here, and you'd have this area in between where they're not connected. And you can actually see that not only in geological features, but also in man-made features as well. There are places out in California where there are fields and fences and things where after an earthquake they've offset from each other and they no longer connect up. Continental drift is the theory of the continents floating on top of the mantle. So that lithosphere, all of those puzzle pieces of the tectonic plates, moving around very slowly, coming together, moving apart to form the actual surface of the Earth the way that we are viewing it today. The first person to come up with the theory of continental drift was Alfred Wegener, German scientist. People didn't really give him much credence. They didn't really believe it at the time because they were not able to prove it. It is now the accepted theory of plate tectonics. And it is the continents are floating on top of the mantle very, very slowly, constantly in motion. Evidence for continental drift. Again, we didn't have very much evidence when he first came up with the idea. We have since come up with a lot of evidence to help support this. So we have the jigsaw puzzle. All of the tectonic plates seem to fit together like puzzle pieces. If you look at the continents, you can see how they would have fit together in the past to form things like Pangaea, one of the major supercontinents, and how they would move together, separate, and how they would fit and form up. The second one is matching fossils. You can find fossils in different places around the world that have no actual physical connection to each other. So fossils on both sides of the Atlantic Ocean that match up. Those show that at one point, those two continents were probably connected. So that's good evidence for Pangaea and for continental drift. Rock types and mountain ranges, same thing. You have similar rock types and mountain ranges on two different areas, but you can tell by taking close looks and measurements and that kind of thing where they would have met up at one time. And then the last thing is taking a look at glaciers and how oceans rise and fall and move into the glaciers and tracks, and you can kind of track all of that and map out all of that. So all of these things are going to come together to give us evidence for the continental drift theory. Pangaea, you guys learned about in the last unit. I'm not going to spend a lot of time on this slide, but you do need to know what Pangaea is. Supercontinent from about 245 million years ago, and then it started breaking apart into Laurasia, Gondwana, which is the two minor supercontinents, and then eventually India is going to collide and form those Himalayan mountains, and then it's going to keep spreading and doing that continental drift until we get to where we are today. You need to be aware of Pangaea. Hopefully you guys remember all of this from the last unit. If not, pause me, take a minute, get this jotted down in your notebook, and make sure you study it because there is stuff about Pangaea on the test. Okay, so the evidence of Pangaea that we talked about, this is kind of pointing that out. You can see where mountain ranges would have connected by these highlighted parts here. Those are mountain ranges that are actually the same. And where they would have connected in the past when the two continents were together. And here it is with Pangaea put all together and what it would have looked like then. You also have the rock types and the fossils. drawn out on this top map here. So pause me, take a minute and take a look at these maps so you can kind of understand that concept and get it solid in your minds. If you need to, you can jot down these pictures, snap a picture and insert them into a Google Doc or whatever so you have it, excuse me, so you can get these concepts straight in your head, because they are super important for geologic history. So we're going to start talking about seafloor spreading here. Mr. Harry Hess came up with the idea of seafloor spreading in 1960, and he said that when magma rises up through the cracks in the ocean floor, it's going to push the old crust out and away and add to it as it cools down. So it comes up and cools, pushing everything further away from it. Evidence we have for this actually came about during World War II. They were mapping the seafloor basically so they could look for enemy submarines and that kind of thing hiding out down there. And they found these magnetic stripes on the ocean floor, and they discovered that if you went to like an ocean ridge, those magnetic stripes were the same on either side. They graduated out in the same amount, and they were positive or negative. So they would face one direction or the opposite in alternating layers, and it was the exact same on both sides. If you had 2 inches on one side, you had 2 inches on the other. If you had 6 feet on one side, you had 6 feet on the other. They were exactly the same on both sides. So Hess decided that that meant that as the magma came up, it cooled, it pushed everything out in both directions. So they can use radioactive dating to show rock ages. And they will also have found that the further you get away from the ridge, the older the rock is. So the younger rock is right there in the middle of the ridge, and as you move out, it gets older and older. So those are how they came up with the theory of seafloor spreading. So if that's the case, and you have all of these layers that are moving out and pushing out and getting older and older as you go further out, why is it that the Earth is not expanding in size? Because we're building more crust here, and it's pushing things out, making it bigger, wider, more crust. As you get towards the opposite ends, that crust is going to sink down. So we have something called the mid-ocean ridge, which is basically an underwater mountain range. It's the longest mountain chain on Earth, and this is where the magma pushes up and forms the new crust. So it pushes up, cools off, forms the new crust, pushes it away. So we have mountain ranges there where it's doing that. And then at the other end, you have trenches. And the trenches are where the ocean floor sinks back down and gets destroyed, melts back into the mantle, and then the whole process starts over. So remember that convection that we talked about before? This is where you're seeing the convection. It comes up at the mid-ocean ridge, pushes out, and then sinks back down at the trenches on either side, and then circles back. So this is it for the notes for today. The homework assignment is going to be all about what you've learned about plate tectonics. There's quite a bit on there about seafloor spreading. That's a big thing on the test, so make sure you understand how seafloor spreading works and what the evidence is for it. That will be a guaranteed test question there. So finish up your notes, take a few minutes and get your plate tectonics homework assignment done, turned in. All of this information is found in the notes that we just did, so you should be able to look this up and get this done using just the notes. If you can't find something in your notes, feel free to Google it and find the answers that way as well. Just double check them and make sure you're getting accurate stuff put down. That's it for today. Once you're done, have a great day, and we will see you next time.